The second hour exam review. That means that on Wednesday, we will have the second hour exam. That's the way most people react. Exam is Wednesday. We'll meet in D204, and we're going to do it there. You may bring a 3x5 card. I will give you a periodic table. Remember that tutorials and quiz 2 must be done by that time. Make sure you bring a calculator. We do have some here, but we're not going to be here, are we? I'm not sure they have them in the other room. So please bring the calculator. I'll do my best to find some if you don't. Any questions? Well, then let's do this. It's going to be a short lecture, just like last exam review, just to stress to you how very simple this exam is. Right? Right. All right, we're looking at a series of compounds with names, formulas, and water solubility. Which one is correct? Okay. Iron 3 chloride. Iron will be +3, chloride will be -1. We would need 1 iron and 3 chlorides. That's not what we have here, is it? The formula is wrong. It should be FeCO3. Second one here, ammonium sulfate. Ammonium, polyatomic ion with a charge of +1. Sulfate, polyatomic ion with a charge of -2. We need 2 ammoniums for every sulfate. The problem here is that this isn't sulfate, is it? This is hydrogen sulfate. That would be a charge of -1. Ammonium sulfate should look like this, so this guy is wrong as well. Calcium sulfate. Calcium is +2, sulfate -2, so the formula looks right. We know that most sulfates are going to be soluble in water, except for barium, lead, and our friend calcium. So no, it is not soluble in water. Aluminum chloride. Aluminum, group 3 metal, it'll have a charge of +3. Chloride, -1, 1 aluminum, 3 chlorides. My goodness, we have 3 aluminums and 3 chlorides? That's not even make sense, does it? Nope, it should be AlCO3. So that brings us down to our last one, which of course must be correct. Mercury 2 chloride. Chlorine, chloride will be -1, mercury +2, that works. Insoluble in water. We know that most halides are soluble in water. The exceptions are lead, mercury, silver, and copper. So, this one is correct. Correct name, correct formula, it is insoluble. Any questions? All right, here we are mixing copper 2 sulfate and barium nitrate. We are going to get a precipitate. That means that this is a double replacement reaction. Because it's double replacement, the ions are simply going to swap. So we're dealing with copper sulfate and barium nitrate. The copper will pair with the nitrate, the barium with the sulfate. Products of the reaction will be copper, nitrate, which of course all nitrates are soluble, and barium sulfate, which is a classic insoluble. A is the correct answer, copper 2 nitrate, and barium sulfate as our precipitate. Any questions? Balancing. Yes, you will have balancing on this exam. Let's look at this. We have 3 oxygens here, only 2 on this side. This is odd, that's even. We can fix that if we simply double, put a coefficient of 2 in front of the iron 3 oxide. So let's do that. Now that gives us 4 irons. We have 1 on this side. We simply need to insert a 4. We have 6 oxygens here, only 2 on this side. We need a 3. And finally, 1 carbon, 3 carbons. Simply put a 3 in here. And by George, we have balanced this equation. Now, on the exam, like I just alluded, there will be a balancing. Please remember, it's just like Blackboard. There'll be little dashes in front for you to enter numbers. If a coefficient is 1, you have to enter the number 1 in the dash. Any questions? Single replacement reaction. What do we remember about single replacements? Very simply, an element and a compound are going to yield an element and a compound. The metal will typically replace the metal. If you have a nonmetal, it will replace the nonmetal. All right, we're looking for the element that will be formed as a product. The metal is going to replace the metal in copper 2 nitrate. That means that the element that's going to be formed is going to be copper. Element and a compound, element and a compound. Looks like this. Copper is the correct answer. If you remember, we did this in lab. We took a nail that was disgusting, didn't look at all like this one, and stuck it in copper 2 nitrate. We wound up with a nail with a copper end. The metal was deposited on the end of our iron nail. Any questions? I told you this was going to be easy, right? All right, this one looks like it could be a real bother. Which of the following is not a redox reaction? Well, remember, in a redox reaction, oxidation numbers have to change. So, let's do this the tedious way. Nitrogen, hydrogen, they're both elements. By definition, they're both 0. Here we have hydrogen. This bonded to a nonmetal. That makes it +1. We have 3 of them, so that's 3 positives. To be neutral, this nitrogen must be -3. All right. So, yes, oxidation numbers have changed. 0 to -3, 0 to +1. This is a redox reaction, and we're looking for the one that is not. But rather than do this for all of these, there's a simple little dodge you can do. Just think about it. If you have an element in either the reactants or the products, it must be redox, because it's either going to change from 0 to something or something to 0. So, element, redox, element, redox, element, redox. Everything, these guys, all of these except D, are going to be redox, simply because they have an element. So let's look at D, just to make sure we're doing this right. Oxygen is going to almost always be -2. We can assume it's -2. We have 2 of them. That's 4 negatives. To be neutral, this nitrogen must be +4. Over here, oxygen is still going to want to be -2. We have 4 of them now. That's 8 negatives. That means that each nitrogen here must be a +4. Nitrogen is +4 in the reactants and the products. This is not a redox reaction. Just remember the simple dodge. If you have an element on either side, it must be redox. Any questions? All right, here's another very simple one. We have chlorine giving us chloride. Is this oxidation, reduction, or neither? Well, neither doesn't make sense because this is an element. We're starting off at 0, aren't we? And we're winding up at -1. So it is a redox reaction for sure. What we remember, though, is that the definition of an oxidation is loss of electrons. So what you simply need to do is to look at this and say to yourself, has chlorine lost electrons or gained electrons? Since it's gone from 0 to -1, it has gained an electron. Not an oxidation, this is a reduction. Any questions? All right, we're all the way to number 7 now. This one looks confusing, but it really should not be. In our reference equation here, 2 A's react with 2 B's plus 6 C's to give 4 D's and 3 E's. We're looking for which one is correct here. Well, we have a mixture containing 2 A's. That's good. It has 3 B's. We only need 2, but it has 3. That means that the B is going to be in excess. That's fine. And we have 6 C's in our mixture. That's just what we need. So, 4 moles of D will be formed. Absolutely. Because we have everything we need to make 4. Only 2 moles of D will be formed. Well, it can't be both 4 and 2 at the same time, can it? So that's wrong. 3 moles of E will be formed. We have everything we need. With D in excess, we can get 3 E's. And that means that both A and C are correct. questions? All right, number 8. We have 0.3 liters of 1 molar solution of calcium nitrate. In this solution, what are we going to have? Well, we're looking at moles and stuff like that, right? We remember concentration times volume gives us moles. Concentration times volume is moles. We have 0.3 moles of calcium nitrate. This guy. So this one's correct. We're also asking about calcium ions and nitrate anions. Let's just review what happens when you take this and put it in solution. Remember, in this case, we're taking potassium sulfate, but the same thing. We are going to take this, put it in a beaker. It's going to totally dissociate. So you take your ionic compound, it totally dissociates according to the mole ratio. So if we go back to our original problem here, 0.3 moles of calcium cations, well, the mole ratio here is 1 to 1, isn't it? If we have 0.3 calcium nitrates, we have 0.3 calciums. 0.6 moles of nitrate. Mole ratio here is 2 to 1. So we're going to double our 0.3 and make it 0.6. In this case, A, B, and C are all going to be correct. Any questions? All right, we're reacting potassium chloride with silver nitrate. We are going to get a precipitate of solid silver chloride. Here's our reaction. It's a simple double replacement reaction. Silver paired with chloride to give solid silver chloride, potassium with nitrate to give us potassium nitrate. We have half a mole of potassium chloride, that's this guy, half a mole of silver nitrate, that's this guy. The question is, what is the theoretical yield? Well, just think about this. There are no coefficients here, are there? Therefore, if we had 1 mole of this and 1 mole of that, how much product would we get? 1 mole. If we had half a mole of each, which we do, how much would we get? Half a mole. It makes sense. And it's correct. B, 143 grams of silver chloride. Well, here is this molar mass. 143 is 1 mole, isn't it? Half a mole would be half of that, 70 something. So that's not right. 1 mole of product? Nope, we just said half mole of product. Potassium nitrate will precipitate, good luck. All nitrates are soluble. And A is our correct answer. Any questions? All right, remember we did a lab where we took sodium hydrogen carbonate, heated it up. We made sodium carbonate, CO2, and water. And we calculated the yield, percent yield. In this particular question, we have 0.25 moles of CO2 that were formed, and we started with 0.5 moles of sodium hydrogen carbonate. Look at the stoichiometry. If you have 2 moles of sodium hydrogen carbonate, you get 1 mole of CO2. 2 moles of carbonate, hydrogen carbonate, 1 mole of CO2. So you only get half of what you start with. So if we had 2 moles of this, we would get 1. 1 mole of this, we would get half. Half a mole, which is what we have, gives us 0.25. And by George, that's what we got. That's 100% yield. In lab, most people got slightly over 100% yield, but still, that was good. Any questions? Dilution. We have 1 more nitric acid. Doesn't really matter what it is, but 1 more nitric acid, 1 mole per liter. We have half a liter of it. We want a final concentration of 0.5 liters, moles per liter. Well, concentration times volume is going to give us moles, right? We have 1 molar, and we have and we have 500 mils of it. So 0.5 liters times 1 molar, we have half a mole. Now we want our final concentration to be half a mole per liter. We're starting with 500 mils. How much more do you have to add? 500. That gives us 1 liter total, 0.5 moles per liter. All right, the next one is a little calculation where you write the number in the box. We have a solution with 0.375 moles of something in a volume of 1340 mils. What is the molar concentration of this solution? Okay, we remember moles divided by volume in liters, it must be liters, gives us molarity, simply moles per liter. All we have to do is substitute 0.375, change milliliters to liters, so divide by 1,000. 0.375 divided by 1.34. That's so simple, I could do it. 0.28 moles per liter. Any question? All right, a pH problem. Everybody loves pH problems. The pH of a solution has increased from 5 to 7. What has happened to the hydronium ion concentration? Remember, something in square brackets means concentration in moles per liter. All right, we've gone from 5 to 7. Has hydronium increased by a factor of 2? By a factor of 100? Decreased by 2 or decreased by 100? This is nonsense. So, when you raise the pH, what happens to hydronium? Remember, it's the negative log, so if the pH increases, hydronium decreases. That's number 1. So we're looking for decrease. pH is a log scale. We've decreased 2 units. That's 10 squared. So we have decreased by a factor of 100. 10 squared is 100. Any questions? There will be some perturbation of this on the exam. Make sure you understand the concept. pH increases, hydronium decreases. pH decreases, hydronium increases. And it's always the factor of whatever it is. 2 is 100, 3 is 1,000, blah, blah, blah. All right, chapter 11. Selenium-80 loses an alpha particle. What does it make? We have a choice. We look at this. We are going to take our mass number and reduce it by 4. We're going to take our atomic number and reduce it by 2. We look at our periodic table. Periodic table that I have here on the slide looks just like the one you will get on the exam. So, we are at selenium. It's right here. Again, atomic number 34. We are going to lose an alpha particle. When we do, the atomic number will decrease by 2, and that will take us downward to germanium. Germanium, atomic number of 32. Therefore, look at our options. Right there in A, germanium 76, so we decrease this by 4, decrease the atomic number by 2. Any questions? Number 15. We have 1 liter of half-molar sodium hydroxide. That's a strong base. 1 liter of half-molar hydrochloric acid. That's a strong acid. We are mixing the strong acid and the strong base. What are we going to get? We're going to get a neutral solution. If you have the same concentration of both, it is neutral. That's right. Well, it can't be basic and neutral at the same time, can it? So this is obviously wrong. How about this one? We're going to mix these two together. We're going to make sodium chloride. What's its concentration? We started off with half mole per liter with both. 1 liter plus 1 liter. What's our total volume now? 2 liters, right? So we have half a mole of this stuff, sodium chloride, and 2 liters. That's 0.25 molar. The volume is doubled, concentration drops it by half. A and C are correct. This one's a little tricky, kind of a cute question though. Any questions here? We're already pushing number 16. You see how fast this can go? Another acid-base problem. We're looking for the hydronium ion concentration if we know the hydroxide ion concentration. We can do this because we know that under all conditions, if you multiply hydronium by hydroxide, you will get 10 to the minus 14 molar. We know hydroxide because it's given. To get hydronium, all we have to do is take 10 to the minus 14 divided by 10 to the minus 5. Don't even really have to feed this into your calculator. You can do this in your head. We have 14, we have minus 5. 10 to the minus 9 is the answer. Any questions, guys? All right, another acid base. Which of these is acidic? If pOH is less than 7. Now this is pOH, remember? If pH is less than 7, it is acidic. But pH plus pOH is always 14, right? So if the pOH is less than 7, that means that the pH must be more than 7. And this is basic. So that's wrong. Hydronium times hydroxide is less than or equal to 10 to the minus 14. Well, that's nonsense. It is always equal to 10 to the minus 14. That's wrong. If hydroxide is less than hydronium, now think about this. If we have lots and lots of hydronium, does that make this solution acidic or basic? It makes it acidic. Hydronium is our acid. If we have more hydronium than hydroxide, by George, it is acidic. All right, let's finish up with a couple gas law problems. We have gas in a sealed cylinder with a plunger. We adjust it so the pressure increases. What happens to the volume? Taking it, we're squeezing it, right? What happens to our volume? This is a Boyle's law problem. Pressure and volume are inversely related. The higher the pressure, the smaller the volume. So the volume will decrease. Think about the anvil landing on the little piston. It squeezes it down, doesn't it? The volume decreases.
So the higher the pressure, the lower the volume?
Yep. Temperature of a gas increases. What happens to the volume? Remember our little friendly balloon that we cooled down with liquid nitrogen and then let warm back up? When it was cold, it collapsed, and as it warmed, it got big again. Charles' law tells us temperature and volume are directly proportional. Temperature goes up, volume goes up. And finally, this is a trivial gimme question that everybody is supposed to get right. Water boils at 100 degrees centigrade. What is this in Kelvin? If you don't remember this, write it on your little card. Centigrade plus 273 is Kelvin. 100 degrees plus 273 is 373. And finally, the one that everyone's been waiting for, the extra credit question. In this space below, draw the structure of 3,3-diethyl 2-methyl-hexane. Chapter 12. We can do this. First thing you do, you look at the parent. You want to draw a zigzag with 6 carbons. So we do it this way. 1, 2, 3, 4, 5, 6. Now we're going to choose one end to be number 1, doesn't matter which. That's fine. And that makes this carbon 2 and that carbon 3. According to our name here, carbon 3 has 2 ethyl groups. Remember, an ethyl group has 2 carbons. We're going to show this in a line drawing as the line going up and down over, it'll have 2 carbons. Ready? Something like this would work. That is 2 ethyl groups, 2 carbon units. Finally, our name says carbon 2, we have a methyl group. The methyl group here at carbon 2 is shown by a single line going up and stopping. Something like this. This is it. 3-diethyl 2-methyl-hexane. And by George, with me talking way too much, we did all of this in 40 minutes. You will fly through this exam, right? Remember, the exam is Wednesday in D204. 3x5 card. Tutorial, quiz 2 must be done. Hang on, don't leave yet. I have something else to say. Make sure you bring the calculator, but I have something else. Here's our tutorials. 1 second. Make sure you do these. Remember, you're shooting for 350 total. Automatically get an A, no final. All right. Hang on a second.